This video will be talking about the Friedel-Crafts alkylation reaction. This is another electrophilic aromatic substitution reaction. And with the reagents we'll talk about here, we can add an alkyl group to an aromatic ring. So an alkyl group being a methyl, ethyl, propyl, etc. Some carbon and hydrogen chain. So let's look at the general reaction scheme first. Again, starting with unsubstituted benzene. We'll highlight one of the hydrogens. And then our reagents here are an alkyl group bonded to a chlorine. So the R is any alkyl group. And that's bonded to a chlorine atom. And then we need a Lewis acid metal catalyst, and aluminum trichloride works well. And that's our catalyst here. So our Lewis acid metal catalyst. And in the product, we substitute one of the hydrogen atoms for the R group. So whatever was bonded to that chlorine. Byproduct is HCl. For Friedel-Crafts alkylation, we follow very similar steps. Step 1 is generating the electrophile. And that's some interaction between the reagent that's not the benzene ring and the catalyst. So when we have an R group bonded to a chlorine atom, of course the chlorine has non-bonding electrons, and we have aluminum trichloride. I already called out that this is a Lewis acid, which means the aluminum, in this case, can accept additional electrons. It's an open shell atom. So when you have the chlorine bonded to the R group with non-bonding electrons, that can create a bond to the open shell aluminum, and then we get a Lewis acid-base complex. So we have the R group still bonded to the chlorine that is now bonded to aluminum. This gives this chlorine a positive charge. And then the aluminum is still bonded to 3 chlorines. Now this chlorine that has the positive charge, let's not forget aluminum has a negative charge. The chlorine with the positive charge is pulling electron density closer to itself. We know chlorine doesn't like to be positive because it's a highly electronegative element. So that pulls electron density away from the alkyl group, and that makes this R group electrophilic. Now, in some cases, that R group bond to the chlorine will actually break. And so you have then R plus and then AlCl4 minus. And that R plus, this is a carbocation here, this can also act as the electrophile. So you might see either one in a mechanism, and sometimes you can tell by the products if the carbocation does form. So either one may participate in step 2, which is generating the carbocation in the ring. So either just the carbocation or that entire complex over there on the left. So let's look at step 2, and we'll actually show both possibilities, just kind of what it looks like if you have the carbocation or not. So step 2, generate carbocation in the ring. This is where we are adding the electrophile. We will show alkylation by the complex, so that first electrophile that we drew, and alkylation by the carbocation as well. And we'll abbreviate AlCl3 minus here. Right below that, we'll show alkylation by the carbocation. And both of these will generate the same intermediate. Okay, so here we go. Written out all of the reagents for the 2 possibilities for step 2. If we show alkylation by the complex, so the one on top, pi electrons from the benzene ring will create a bond to that R group, to the alkyl group. And then the bond between the alkyl group and the chlorine will break, and that chlorine will gain a pair of electrons. This is actually a reversible step, so let me fix the arrow. Let's draw the product, and then we'll draw the arrows for that other possibility. So here I've shown the pi bond on the bottom right breaking. So I will say that the carbocation ends up here, and the R group ends up on this carbon. Now you know you could show either carbon having the carbocation because this is a ring, as long as they're the carbons adjacent to each other that were part of that original pi bond. Either one is okay. So what I've just highlighted in green. And then our other product for this step is AlCl4. I'm emphasizing the chlorine because that will come into play in the next step. Okay, so that's if we follow alkylation by the complex. Alkylation by the carbocation looks very similar. We just have one fewer arrow. Instead of having to break an alkyl to chlorine bond, the electrons can just directly bond to the carbocation, and you end up with the same product. So now that we've generated this resonance stabilized carbocation non-aromatic intermediate, our step 3 is removing the beta hydrogen . And for this step, the electrons that are in the bond, looking at this byproduct here, the electrons in the bond between the fourth chlorine, really, that was added to this molecule, but one of the chlorines and the aluminum, those electrons are used to create a bond to the beta hydrogen. So we show the arrow starting at this bond, ending at hydrogen, and that forms a new bond between chlorine and hydrogen. We get our HCl product. And then the electrons in the bond from the carbon in the ring to the hydrogen will then reform a pi bond, and we get an aromatic ring as a product. So this last step, we have our final product, where we have the R group added. We have HCl as a byproduct, and then we've regenerated the catalyst. So again, a very similar mechanism to what we've seen for all of the electrophilic aromatic substitution mechanisms.